they cannot wait to tell how things connect to each other, right? So they are like up there, and they really cannot get down and talk about actual uh, like computation or like actual process. They really want to stay up there and look at everything from like the bird eye view. Okay, and Dr. Gross is one of those, and at the yeah, so he's one, and there was another one at grad school, Indiana University, and his name is Michael Larson, and he's one like that. And Hari Brakovici is an analyst, he's like that. And I mean, these guys would come without notes and then teach graduate courses, and then he can customize it. I remember first time in the grad school, they had a program for us to like for algebra, and so Michael Larson came to lecture us, and like 5 minutes before the class begins, this one guy, Adam, he asked, actually, we haven't done field theory. Can you go over it? Like, oh, and he said, like, some of us haven't done field theory in undergraduate. Can you go over it? And he was like scratching his head and walking back and forth, back and forth. And then he talked about like the kind of the overview of the field theory course in like probably 2 hours, 3 hours, and he proved most of the things. And then then at the end apologized that, I'm really sorry if this wasn't good because I didn't have much time to prepare. And like we are, all of us are like in awe, like, how does this guy can do it? And yeah, anyway, so Dick Ross is like that. He has everything really. Yeah, he's up there. And yeah, there is another guy that's like that. He's in uh, you should watch his multivariable calculus lectures. I watched like one or two. He's I was teaching it, and then I asked students to watch him. He's a guy in geometric Langland program, and he has the difficulty of kind of getting down to the level of the students. And I forgot his name. Yeah, I mean, when you that lecture is good to listen if you have like learn more, and then like he would explain these things from the higher point of view. He comes down, and then this is at Berkeley, and yeah, students are like say like, can you do some computations? And like, yeah, just keep, but you get to see the multivariable calculus course from like the highest point of view. So I think this is important. He's an important person. Now, what I'm gonna do, in this, when all this is in your background, and also you have AI. So if you ask anything, and then it'll tell you. So now in this day and age, I use AI, but like for example, if I created a bunch of posts in Piazza, so I'll say like give me these things, and then it's like much easier. And but typically, if I create something with AI, I do more work. I write more things than the AI does at the end of the day to get it to do what I want. I'm using it as assistant, and I fully understand the capabilities, and yeah, and so uh, like when you train AI, so there are people who write graduate level or like advanced undergraduate problems for AI to solve, and that becomes the data. And I was doing that too for a while when I came here. And so AI at the moment is can get the A in any course, but cannot get an A plus. So I'll repeat, like can get an A in any math course, starting from like undergraduate all the way to like graduate third year, second year, third year. Okay, so it can get A, but not A plus. So yeah, so it's hard to write those problems. Uh, I mean, you write them and then you evaluate the answer, and then you kind of yeah. So that becomes the training data for AI, and it's pretty out there. Okay, now my approach. Let's go back into here. This plan. So these things, and then you have AI. And it is, I mean, I developed this institute, uh, and kind of the main point is I'm going to teach uh, students to like prove theorems, and I'm doing this thing in the age where uh, AI can do it. Okay, and then it's going to happen very soon, and I'm actually, I mean, I have some ideas and this and that, like, but it just feels like in the surface, it feels like we're just throwing in the talent into like a useless course. Okay, so that's in the background too. But yeah, so use this thing. Okay, so you're free to use this thing, but careful with one thing. So when you use AI, uh, your brain atrophies. Atrophies means it shrinks and it stops thinking, right? So in Sinhala we call it atakuna. So so if you use AI, then your brain is not working, right? So you have to make sure that your brain is working. Okay, so when you for example when you solve problems, just don't use AI. Okay, and use AI. I think a good thing to do is use AI for the purpose you used Google. Okay, so with Google, like the way I think about it, like back in the days, I used, if I want a reference or like something about a topic, I would Google several things and I go through the article, then I find out what this thing is, then I Google again, and so on and so on. That replaces going physically to a library. And now with AI, what I can do, I can like write this thing and then I can update the prompt and like fetching all the things from Google and all the sources and compiling it into a readable manner. That's done by AI. Okay, so I think it is okay to use AI for that purpose, but don't don't the keep the kind of the core, like thinking part of the work to yourself. Okay.
Okay.
Okay. So now let's go again. So the next thing is, so my is this. Now, people might say that these are like too advanced, uh, but but you can ask. You can. I mean, these are like typically very advanced things, and only a very few people, only very few students learn from a university. And so you can ask them this question, like in a place like UCSD, it's a university in uh, California, and the abstract algebra class, this class, okay, not the linear algebra, the abstract algebra. This has more than 200 students. Okay. Repeat, this is like one university, UCSD. More than 200 students are taking this course. Okay. So somebody knows the value, and it's not, yeah. So yeah, that's it. It's actually very kind of scary to think that this much, because the way when we learn things, when we went through this thing, it was like very few students did this type of math. But when you see a university with like 200 students doing abstract algebra, then you go like, okay. Now my plan. This is my plan.
Video post. I don't know if it's my fault or it's from the uploading side.
Recording stopped. Recording in progress.
Okay, you guys can see this, right? So the call got dropped, right?
Yeah.
Yeah, actually, can I see you guys' faces? You can. I mean, it's really nice to
Mm.
see the reactions and everything. You can keep the, yeah, thank you. You can keep the mic muted, but it's good to see the reactions. Okay, okay, so, okay. Uh, Now, so this okay, thank you. Hasindu is there. And this first mountain is like linear algebra, and then you climb this other one, called abstract algebra. Okay, so typically students would like learn this and then learn this. I mean, there are topics that are taught in like abstract algebra that's not done in linear algebra and vice versa. Okay, so and this is what happens. So, and you can follow these main routes by going through those lectures. Okay, so thank you very much for turning on the camera. Now this feels much better. Okay, much better, much better. I can see you guys. Okay, now what I'm gonna do, like I'll do something like this. So I'll start like somewhere here. So think of this as like smaller mountain, and then you have larger mountain, and there are well-defined paths to climb these. Those are the video lectures and all the textbooks and everything. Okay, so I'll just do something like this. Okay, good. So in this way, like yeah, I mean, to tell you the truth, this is how I teach anyways. So you're gonna get confused a lot typically, and then you kind of uh, figure things out, and then you get unconfused and you learn a lot. Okay, so I believe in like yeah. So the think about like you have the pool, you have a pool, and some people like to uh, some people like put kids in here and with the safety and all that, and then you teach how to swim. Uh, I am the kind of guy who'd like put you guys here. Okay, you learn quickly, but okay. Yeah, and okay. Now let's start. So uh, so it's kind of this coupled with this one coupled with not instrumental like the relational. I would throw you guys in there, and then I talk about the relationships with this thing with the other stuff, but won't go in and do computations. I will do it, but I'd spend more time on like telling how this connects to every other thing in like the world of mathematics and but you get it. You get something, and it works. I know it works, and I have like students and who went on to like you kind of get a brand out of it. Okay, now let's let me do something now. I have prepared some parts of the lecture. So for example, so you guys have access to the piazza. So in the piazza post, I have some posts in there. So let's so what I have done. So start. So the first section is solving linear equations. Solving systems of linear equations. Okay. Now, let's do this example. Let's say we have so we have this equation. So x equals 2, y equals 5, z equals 7. Okay, and of course, like this is kind of the after you solve the equation. Okay, now before you get here, typically what happens, you'd have a step above here. So we have x plus y plus c, x plus y seven. Okay. And let's say this equation. Let's say we had y equals 5. No, let's say you have x plus y equals 7. 2y equals 10. And z equals 7. Sorry, this is boring, but the things can get complicated. Okay, so we'll do this thing, and then you look at from like kind of from the bird eye view. Okay, from very top. Okay, now the last one. Let's say we had the equation 2y equals 10 and x plus y equals 7 and z equals 7. Okay, good. Now, so this is the starting equation. Call it 1. Is the starting system, and then you move to the second one, and then you move to the third one, and then you move to the fourth one. Okay, and if you're given here, you'll probably follow these steps, right? So in the first step, what you did, you actually switched. In the first equation doesn't have x, right? When you have that, you flip, you switch the rows. So you change row 1, interchange row 1 and row 2. Okay, good. And going from system 2 to system 3, what you did, you replace the second row by half of the second row. Because you have 2y equals 10, you want to find y equals 10. Okay, so the R2 get replaced by half times R2. Okay, now in the third step, what you did, you're kind of getting rid of this y from the first equation. Then you're replacing R1 with R1 minus R2. So this R stands for the row. So you're replacing row 1 with row 1 minus row 2. Good. Now So these type of operations, like what you did here, these are called basic row operations. So elementary. Replacing a row I with row j, exchanging rows. And replacing some row some ith row with the scalar of the ith row. C is not equal to 0. And then the third operation, let me write them like this way. The first one, we are interchanging rows. So the ith row get switched with jth row. Okay. Tirath, you okay? This is okay, right? Okay. And then the second one, you replace some row I. It's some multiples of row I where C is not equal to 0. And then the third one is you're replacing the ith row by Ri plus some C times R2, Rj. Okay. So these are the basic row operations. Now, so I have given you some examples. In Piazza, go through the go over the examples. So this is example exercise. Let's don't submit this thing, okay? Exercise solve the equations from Piazza. Okay. Now, now I will ask you these questions. So I'll ask you the question. If I give you any system, okay? If I give you any system, can you solve any system? With these basic row operations. Okay. Can you do it? Hasidhu?
I think yes.
Yes, right? And yeah, so the answer is yes. Now,
But if there were like X, Y product term, you can't do it, no.
oh. So, very important question, okay? So, these are called a system of linear equations. Okay, so the equations are of this format. So equations are of this format. Let's say they always have they don't have product terms. You have like equations that looks like this. So the equations, we'll define this thing later. I mean, in a bit, but let me say it. So this linear means equations that looks like this: 3x plus 5y plus 8c plus 9w equals 7. Okay, there's no product terms, just a sum of terms. X power x, and there's no product terms or no powers, and you have coefficients in front. Okay, good. Now, here is the question. Here is the actual problem. So this is the exercise 1, and you submit this thing. Okay. So the problem is so the problem with it's like, solving these equations, and you say that, yeah, you can solve it using the basic row operation, but there is a problem. The problem is you actually look at the equation, and like the kind of the path that you take kind of depends on the equation. Okay, but I want you to write the algorithm. It doesn't have to be programming, but like clear, detailed steps that using basic row operations to solve any linear equation. Okay. Okay. So, write an algorithm to solve any system of equations, system of linear equations. Okay. Good. And when you so go through the examples in the, like, manually solve the examples that I have given in Piazza. They're like simple systems, but they are designed so that you'll explore all the different cases. Okay. Good. Go the examples from here. Good. Now let me do some. So when you solve a system, so let's see what you like when you do this this type of these processes, like row operations. There is something that you are kind of there's like end goal that you're not exactly familiar with. Okay, so for example, roughly, so let me talk about. I think this is a doable problem, and so what you have like once you get to the end. So let me write the equation. Okay, so So this example, x plus 2y equals 9, and c plus 4w equals 5, and let's say 12t, sorry, t equals 7, and yeah, t plus u. Okay. Think about this equation. Okay, so let's say you solve it and then you get to here. Okay, so this is a system with like 5 variables, x plus y, du. Okay, and let's say there is another one, t plus u equals 9. Let's say you get into this setup, right? So let's kind of study this thing. So we have, so the first equation has x, right? And none of the other equations have x's. So we have gotten rid of the x's from the other equation. Okay, good. Now, where's Kisela? Oh my God. එත්මික කියන්නේ කිසලමද?
කිසල වෙන කෙනෙක්.
Huh?
කිසල කියන වෙන කෙනෙක්.
What happened to Kisela? Komunika.
I don't know, I'll ask you.
Okay, it's okay. It's okay. Now look at this thing. Okay, so this is interesting setup. So we have x in the first equation, and we have gotten rid of x from the rest of the equations, right? And you know that you can do this thing, right? And now, how about y? There is y here, and you really cannot do anything about this y. Okay? If you do some row operations, then if you try to do row operation, then yeah, you can't do anything about it. Okay? Because if you try to, there's no way to get rid of it. Okay? And then, but this C is nice. Right? So this C we can use to get rid of what's below. We can get rid of C from all these three equations. We had 3 equations, and we can get rid of C from the last 2 equations, right? So that's what happened in here, right? And also you can get rid of C from the first equation. without changing x and y. Okay. Right. Similarly, this now if you look at the w's, so the w, just there you can't do anything about it. You try to do something about it, it's gonna mess up C. Okay, good. And now let's see this t, right? And with this t, there's no t's above. So all zeros. Good. And also C, right? But this system is not fully solved yet. There's one more step you can do. What is it? So if you have this system, there is one more simplification you can do. What is that? Anybody? Kisala? So you can get rid of. Okay. So this is important. So at this level, what you can do? What can you do? Kirat. So what can we do at this stage? Oh, is this too difficult?
It's just t, the third and the fourth equation, t plus u equals 7 and t plus u equals 9 doesn't have any solutions. And so
Yeah. So that's
I'm
a
trying
that
to understand what
yeah,
I
yeah, yeah. Okay,
am
that's a
trying
that's a step ahead. Okay, but so that happens when you
yeah.
look at the right hand side of the equation. Okay, okay, but there is a simplification you can do in the left hand side. What is it? So now, if you look at these two equations, you can try to get rid of t from the second equation. I mean, that's what we've been doing. You had x and you got rid of x and so on. Right? So from this, you get one more step. And let's say we have this x plus 2y plus 2w minus u equals 9. Then you have c plus 4w. Now t plus u equals 7. And if you subtract the, if you do the operation r, we replace row 4 with row 4 minus row 3. If you do that operation, then you get 0, like this side is 0. equals to. Okay. 0t plus 0 equal. Okay. So what's happening, like, and once you see this thing, you know that the left hand side is 0 and the other side is 2. So no matter whatever the values you take, let me write out the full equations. See 0c plus 0y, 0x. Okay. So that's the last equation. So this one has no solutions. Okay. So the original system doesn't have any solutions. Okay. But in general, I mean, if this was instead of 7, if we had, if instead of 9, if this was 7, then this would be 0. And the last equation would be like perfectly fine. Okay. Good. Now, so when I say that I ask you the first question, exercise 1, to write an algorithm to solve any system of linear equations. Now we can like update this problem. Okay. We can update it to say that if you have any system, you can write an algorithm to get it to this format. Okay. So this format is called row reduce echelon form. So let me write down the like what we have here. Like I'll write down just the coefficients. Okay. So we have 1 here, and it's nice to write it this way. Have 1, and then you have a bunch of terms like this 2, and then you have another one. So what we have a 1, and then you have another one, and another one, and all zeros. So we have 1s here. And these are called pivots. You have 1s, and all zeros, if you have like rows with all zeros, they go at the bottom. Okay. And each row, the first non-empty, first non-zero entry is 1. Okay. And so this first non-zero entry is called the pivot, and the pivot in the row above is always happens in at a smaller place than the one below. Okay. And above these pivots, you always have zeros. Good. Okay. Now, so exercise 1. So let's update it. That any take a system, consider a system of linear equations, system of linear equations. Let me write it like this. Given any system of linear equations by applying basic row operations. We can get the right hand side of the system to reduced row echelon form. Okay, I'm sorry, like I'm not writing things in like mathematically yet. Okay, so I'll do it in a bit, but at this step, I just want you to like write algorithm, okay? And use the basic row operation to get here. Now, any questions so far? Questions?
What's RRE?
Oh, row reduced echelon form. It is this one. Okay, and I'll put the kind of the, we have to write it in a little bit detail. Okay, but this is, yeah, this stuff you look up. And I'm not writing it properly because I haven't introduced the, actually I haven't introduced the matrices even. Okay, but this one, this is good because this is something like, like, that you can solve linear equations, but I'm asking you to write an algorithm for this. Okay, and then let me ask this thing, exercise 2. Show that your algorithm from exercise 1 actually stops in finitely many steps. Okay, this is important thing to do, and I'll add something here. So look up halting problem. So this is where, so like if you have a program, like you write algorithm, and you have to kind of, there's no substitute for proving that it converges, that it stops. Okay, so the halting problem says, like if you take a, like probably most of you have written programs, and so when you compile, it picks up all the syntax errors, right? And then sometimes it picks up, this program has a loop and we're not sure that it's going to stop or not. Okay, and you think that you can write a compiler that detects if the program is going to come to an end without actually executing it. Okay, this is a fun little theorem. It's a very small theorem. And that theorem tells you that there are no such compilers. You cannot have a program, meaning a compiler, that output, if a different program would halt, meaning like give output without running indefinitely for any given other program. Okay, and this is a fun little problem, but this kind of justifies the exercise too. But it, like in general, if you write something and I mean to get this thing like properly, like get up to the proofs level, probably you need like induction and so on to way too many times. But don't need to get into that level of rigor. But make sure that this your process algorithm goes towards something. Okay, and good. So, any other questions with this? So here is another one. Let's say uh, like two people have like different algorithms and they both take the same system of equation to the row reduced echelon form. No, yeah, they both bring it to a row reduced echelon form, like the final format. And can you prove that those two are the same? Let's say Aditya come up with the algorithm and it only uses the row reduce uses the basic row operations and gets to a row reduced echelon form. And Kisela does the same, and his algorithm is different, right? And can you prove that those, even though the paths are the way they both of you solve the equation is different, but do you get the same? Do you get to the same system at the end? Okay. If two different algorithms starts with system A, then they will end in same they'll end in like same final format. Okay, good. This is something important to know. Right, so the now do you have any idea how to prove this one? See, like now is it true that now the things are like getting more abstract and difficult? How these things are like still trivial? Is this okay? So are these things trivial or Hasindu, is this trivial? Hasindu? Komika.
So,
Yeah. So is this type of questions, are these like trivial or like what's going on? Are you completely lost?
also, we have to think about
Okay.
another time.
That's good. So this is not easy. Right. So the so what we're doing, we take something very like very mechanical, right? And then you ask uh, very interesting and like deep question that the normally if you're an engineer and you want to get this thing done, you have algorithm and it works and it gives you the solution and you run it and you're done. Okay, good. So, but now these are mathematical questions. Okay, so let me tell you a story before we actually move to matrices. So, story. This is a very good story. Okay, and fluid. This will get you like the kind of the uh, taste of like what we're doing now. So here is the situation. You take a cup of water, cup of water. You take a cup of water, and then you kind of mix it, and then you set it aside. You take a cup of water, you mix it, and then you leave it to settle. Okay. Now, so there are like three types of people who look at this thing. Okay. So you have physics people. Okay, and they use the like the laws that they know about like motion and everything, and they come up with the equation that describe the fluid motion. Okay, so these are called Euler equations, and the next one is Navier-Stokes equation. Actually, one that works for this setup is because this fluid has some viscosity, so the equation that really models this thing is called Navier-Stokes equation. So they have that, and also uh, they run experiments, and then they come up with laws. They measure like this is going to take this much time if you start with this and that. So these guys produce laws, and then you test it out with experiments. Okay, good. Now, they have the computational people. So they would take the equation, Navier-Stokes equation, and they would like create approximations of the system, and then you run numerics, and then you come up with solutions, approximate solutions. That describes like how the, how things works out. And this is not a this is something that really happened. So the situation with the cup of water and liquids, the same equation works for the like the in the earth and the wind. Okay, the wind. And the way people do weather predictions is by actually working with the Navier-Stokes equation. Okay, and the trick is they cannot predict the weather like in month in advance. So they do approximations, and so they pay by not being able to predict forever. Okay, good. And now in the math side, we have a so in math side, so the math people ask this question. Uh, they ask if you take this cup of water and you shake it and you let it sit, okay? And now, if you're modeling this fluid motion using Navier-Stokes equation, right? And so the Navier-Stokes equation, I mean, it's kind of like you can think of it as a uh, complicated model that describing something similar like throwing a ball. So when you throw a ball in A level, you know that if you know the initial velocity and you can compute the trajectory, right? You can say that if you throw it from here with this velocity, it's going to land over there, right? And so the math people, they take the equation and then you take some initial condition, meaning like initial setup that the fluid is at. Now the question is, any guess? The question is whether this glass of water, whether the water in the glass, is it going to explode or not? Okay, is it going to settle eventually? Okay, the question is this going to settle eventually? And this is not a small problem. This is one of the 7 millennium problems. Okay? And it's more interesting, I think. You'll get to see, I really think that you guys will get to see the solution of this thing with this problem settled. So the current status, this is like a couple years ago. One guy from Italy, Tariq El-Gandhi, he proved Euler equation. Euler equation is the equation that doesn't have friction. Okay, he showed that for the Euler equation, this thing actually explodes. You can have nice initial condition that explodes in finite time. Okay, and so that's the kind of thing that we mathematicians think about. Okay, and what else? There's one more thing I need to tell you. Yeah, so with the Navier-Stokes equation, we have proved there is a proof that, like in the, let's think about the, so this is the Earth, and you have seen tornadoes. Earth, and you have seen this type of tornadoes. You know what I mean, right? So we have proved for the Navier-Stokes equation, if a singularity happen, if something, if like, if this thing blows up means like the fluid starts to move faster and faster and faster and get to infinite speed. Okay? And we have shown that like the places where such infinite velocity get created is going to be at most one-dimensional, meaning that the fluid cannot blow up in a planar region, for example. Right? So it can be happening in a line like this, like in the case of a tornado. But the thing with the tornado is like it's get to like really high speed, and then with the friction, this like all the tornadoes that have happened, they kind of died off. Okay. So, but this is progress in Navier-Stokes equation. We have reduced the dimension of the singularity. Okay. Very, very, very difficult. But yeah, these are fun. Actually, a lot of harmonic analysis goes into solving these things, like analyzing these things. And yeah, yeah, once you go through analysis, harmonic analysis, then you actually can attack this type of problems. But they're not about like computing or like experimentation, but once you have the tools, you can really work on these things. See, like you already see the distinction of type of questions we ask. Okay, if this was some other class, you'd say like, okay, you do row protection and then you get to this format, and then you learn how to like look at the right hand side and left hand side, and write down the space of solutions, or like determine uh, if the solution set is empty, or like the solutions does not exist. That's the end of the story. But for us, that's like the beginning of the story. Okay. Now let me draw a picture. So now, so picture again. So so like earlier, the earlier we started with one equation, one system, right? And then like kind of our point of view, like we are focused on like one equation, right? And we are applying the algorithm to that. But then we notice that actually we are changing the system. Every time we apply these elementary operations, we are changing the system. Okay? So what you're doing, you can think of as like, if you think of this is like the set of systems, just the right hand side, okay? Because that's what you're interested in. So if you look at all the right hand sides of all the systems, okay? So m by n. let me replace it. So this is the set of right-hand sides of all the n by n systems. Okay. So we started with this one right here. Right, so this is what we started with. Okay. And what happened, we have like first system, and then you have the second system, and third, and fourth. And actually the fourth one is in the correct format. Okay, good. So the picture is this. So we started with equation 4, and we jumped to equation 3, to the system 3. Okay, and then you apply another operation, we jump to equation 2, right? And then you jump to, wait, what am I doing? What we start with 1. Okay, so we start with 1, first system, and then you jump to do a row operation. Now you have whole different system. Okay, and then you have another one, and then you have another one. Okay, and the fourth system is the one that we like. Okay, and then if this is the set of all the equations, so set of, for example, if this is the 3 by 3 systems, right, and this is the one with the identity, right, 1, 1, and 1. The coefficients of x, coefficients of y, and coefficients of c were like 1 and 1 and 1. So we ended up in here, right? And now you have this picture that like any system, like they would kind of, when you apply the this row operation, they would like kind of jump into here. They'll like hop finitely many times, jump finitely many times, and land in here. Okay, good. So there are a lot of equations that gets into here. Good. And let me write this thing in blue. So these are like your these are your like row reduced echelon forms. Right? So when you solve system, when you say that you can solve it, what you're saying, you're describing something like this. Like if you have the kind of higher level view, you're not like stuck in one equation. You're looking at the space of equation. The first thing is, you know that you're changing the system. Okay. Okay. Now you're trying to find solutions for the system, and you're changing the system. I mean, at this point, you might ask, what you ask this question? uh, uh, there is another question that's like, it's so fundamental, and you have been solving these equations forever. You don't even question to ask that question about it. So when you change these systems by doing row operations, and if your goal is to find the solutions, we have to kind of prove like one thing, which is we have to prove that when you apply row operations, you don't actually change the solutions. Now you look at it from this level, you kind of have to ask this question, like what's happening? You're doing the row operation, you're changing the systems, and you're using this process, but does it actually preserve the solution? Okay. And the other thing, like the question 2 that I asked, question 3, exercise 3, and this is about like when you go when you go along this path, if you start with some equation here, you apply row reduction, would you land in the same row reduced echelon form? Okay. So it's kind of like you want to say that this space of this set of right-hand sides of m by n systems, they're actually kind of well separated. They don't like kind of they stay in their own orbit. Okay. So the exercise 3, I mean, I'm talking this stuff, but we're gonna introduce the notations, and you're gonna actually prove all these things, okay? But I'm like getting you started in the way of thinking. Now, so in here, so the picture that we're after is actually something like this. So we have the m by n systems, and we want to have some sort of like orbits, and they don't cross each other. Okay, and they have and each orbit has a unique element that you call the row reduced echelon form. Okay, and your algorithm is a way of telling where to go at each step. So the algorithm tells you, if you're here, go this way to go get here. Okay, and if you're starting here, it tells you to go this way. Okay. Now, good. So we get here. So mathematics is the study of structures. Okay. Good. Now it'll be really nice there was a kind of well-defined structure to describe this setup. Okay, so like when you solve equations, you're not looking at individual one. Right? In you do mathematics, you just see like, okay, so this is what's going on. And this is a well-known thing, well-known object that we study. Okay, and this is called a group action on a set. Okay, and I want you to view it this way. I want you to compare what's happening here to this. So let's draw this picture. This is very familiar one. So when you do, you get your hands on a Rubik cube. Okay, and it's not in the form that you like. It's like all scrambled up. Okay, and what you're doing, so this then you kind of do operations on this thing. This one hand, and you have the both hands. 1, 2, 3, 4. Okay, so these are your operations. You're doing some operations, and probably there are like basic ones. You rotate this, and you have like basic operations in this setup too. Okay, and this is your object that you're manipulating. So in this case, your set, so you're looking at the set of all configurations. Okay, so when you take the Rubik cube in certain state, and then you apply operation, then it changed into something else, right? And you keep doing this thing, and then finally you get to the solution. Okay, so in this case, I mean, if the Rubik cube is originally has the as a solution, and you scramble it, and then you can always get back to this. Okay, and in the same way, I mean, the situation in here, you have the set is the set of all systems, and the operations are what? The operations are basic row operations. Okay, it is very important that you kind of understand the group in this way. It's something like you're doing. It's good to like define a group with the intuition of group actions. Okay, good. Now, let's take a. So what's the time now? 11. So let's take like 10-minute break. Okay. Good. So let's take a 10-minute break and then we'll go back. Good. So I will stop share and then I will stop the recording too for now. Are you guys there?
Yes.
Okay. Can I see the faces? Okay. So how is this? Is this okay? Let me not record it.
Reply to that question.
Okay. Now, let's look at this. Okay. So I mean, we'll go through these things a lot, but so the one that you saw in here, like group action on a set, right? You have basic operations and it act on a set, right? So the operations that you do, like typically they form these nice algebraic structures. Okay, for example, in here, if you do an operation, you can also always undo it, right? With the Rubik cube, you do something and then you twist back and then you back in the normal place, right? And then if you do, you can like combine operations, two operations, right? And then you can, so yeah, there are things like that. And there is the operation of like not doing anything, which is the same as like doing something and then moving back. You can kind of do the inverse, opposite of operation. Okay. And those are like very, when you think about it, those things are everywhere. And but you're not looking at that abstraction. Okay, so there are basic basic structures. So We'll go through these things in detail, but for now, I have listed everything. So have something called monoid, group, ring, field, module, vector space. So what we're dealing with, we're starting with the vector spaces. But these monoids and groups and rings are like much simpler than vector space. Okay? And you have algebras. And the main thing that you're studying is in the linear algebra, it's actually it's actually an algebra. Okay? The and then you have, these are like we don't study, but I mean we do study in our product spaces. But these are the things you run into in typical undergraduate curriculum. And each of these things is like a whole course. Okay? But it's good to like learn the definition and what it does from the very beginning. Like think about this setup. Like this is actually a true story. I went to Ananda College, right? And my English was terrible, right? And so you have like those sentence patterns, right? And you learn it like, you learn one in 1 year, and then the next year you learn the next one, and so on and so on. In between you have like, poetry and drama and all that stuff, and then right, this three, I think it was 3 months before before O levels, and I finally went to Narada Dinasena. He was a teacher, was doing spoken English, and I went there, and then he just did all the sentence patterns like there, like I don't know, 12 or 15 of them. He did it all at once, and it's very simple. I can like take a sentence and like switch it to like 15 different things very easily. So you don't have to wait till the another year to learn the whatever, like past participle or whatever, right? So you can learn, you can know everything. Uh, can get a rough idea of it, and you go deeper into each one of those later. But yeah, that's how I feel about these things. And when I talk, I will actually, I won't be able to stop talking about the proper thing. Okay, so I want you to let's go. You can see it clearly, right? So now let's look at uh, uh, so what do you let's take some examples. Let's say what is something, like integers. Okay, so integers have, you can add, you can multiply. Okay, so in that way it has like two operations, addition and multiplication. Okay, and if you think about like twisting a Rubik cube, right, it's kind of like multiplication. You do it and then you do it again, and you're not adding two of the things. It has the feeling of multiplication, right? So that one will ended up being a group, right? And the integers, that's actually a ring. Okay, the ring has like two operations. So uh, the we have to like write things down and everything, but so the group has uh, only one binary operation. Okay, so we call that the multiplication, and it has inverse and then identity, and you have something called the associativity. But when you have something like integers, you know that has two operations, and it's kind of good to look at the rings, and that's the one with two operations. And if you have the with integers, if you multiply two integers, and there is something called like there is a idea called an identity, meaning that when you multiply with that, you don't change anything. Okay, so in the case of integers, what is the identity for multiplication?
One.
One, yeah. Right, so what would be the identity for addition?
0.
Yeah, that'll be 0, right? So there's element. Now, then you can, there is something called, the idea called inverse, meaning we have an element, there is, there's another element that when you multiply or like add, you get back to the identity. For example, in the case of integers, so let's say you have the element 5, and you're dealing with addition, is there an element that you can add to bring it back to 0? Right, so that would be the -5. Right, so in rings, addition has an inverse. But how about the multiplication? If you take a non-zero number, non-zero integer, do we have an inverse for that? We take non-zero integer like 7. No, right? We don't have an inverse for that. I mean, the one that we have is 1/7, but that's not part of the ring. Okay? So and then you have things like, I mean, these things are like very, very like ingrained in our, in us, because, if you have a expression like A bracket B plus C, when you remove the brackets, you have like AB plus AC, right? And that's a property we like, and we have like, learned it for like, since we're from the, I don't know, age 5 or 6, whatever. But not 5, 6, but that is a property you want, and that's a property we have for a ring. Okay? And that's called the distributive property. And now when you think about real numbers, right? When you think about real numbers, if you think about addition, if you think about multiplication, so the real numbers, if you take any real number, do you have a multiplicative inverse for the real numbers if it is not 0? We do, right? So it is the same with rationals. If you take the set of rational numbers, it has the addition and multiplication. So it's a ring. Okay, addition and multiplication with like a whole bunch of properties that I didn't specify, but this the ring of reals, that's very nice. It has the additive inverse too. It has the multiplicative inverse. So if a ring has the inverse and multiplication, then we call that a field, right? And the field comes in nicely, like when you write down these equations, systems of equations, and if you have like 2y equals 10, you want to be able to get rid of 2. You want to multiply by half. So you want to like the whatever the 2, that's the coefficient, and that coefficient we want it to be coming from a field rather than a ring, because sometimes you want to divide it, get rid of it. Okay, good. Now, so you have the addition, multiplication, and if you think of like vectors, so with the vectors, you can add vectors, right? But you cannot multiply vectors. So the multiply, I mean, when you multiply two vectors, you ended up in you want to get a vector. Right? There is something called cross product, but it doesn't satisfy what we want. So in general, with vectors, you have addition, you can add vectors, and then you can multiply by scalars, not by elements from the set itself. Okay? So basically we have like three types of operations, and just multiplication, addition, and scalar multiplication. Okay? And I'm getting stuck. So if you think of the matrices, I know that you have seen 2 by 2 matrices. Okay, in A level. Now, matrices you can add. Okay. Matrices you can multiply. 2 by 2 matrix, you multiply, you get another 2 by 2 matrix. And also you can multiply a matrix by scalar. Okay. It has all these three properties. And so the kind of the funny thing is, if you look very carefully, like what you're doing in linear algebra is you're studying the algebra of matrices. Okay. So now but the thing is like that matrices has too much structure. Okay. So if you think of matrices, and you can add, right? If you just take the addition of matrices, that would form a group. Forget about the multiplication, scalar multiplication. Okay. And if you think about matrices just with the addition and multiplication and forget about the scalar multiplication, then you have a ring. Okay. And if you think about matrices, just addition and vector spaces. Addition and scalar multiplication. And forget about like multiplying matrices. If you think of matrices and only those two operations, you have vector space. Okay. Now here is the approach I'm taking. When I teach, when we run into a theorem in linear algebra, okay, I will ask, we will go through the book, right? But every time I run into a theorem, right? Let's say a theorem about vector spaces or matrices. Matrices are the same as, not like pretty much the same as linear transformations. Okay, so you'll be studying vector spaces and algebras. But every time we run into a theorem or like a property, we'll ask the question like, is this really a theorem about matrix algebra, or is this simply a theorem about a group or a ring or a vector space? Okay, good. So in this way, like we are learning linear algebra, but at the same time we are kind of at each proof we are like seeing what's really going on. Is this like a theorem about matrices, or is this a theorem about whatever, like linear transformation? So is this simply a theorem about a group or like a monoid? Okay, in that way you learn things, but you kind of get kind of seeing what are the like the minimum assumptions needed for that property. Good. So that's why I have all these basic algebraic structures, and we're not going to be using the other stuff, but no, I might talk about, but I'll talk about the categories. Okay, we'll get to that later. But now, so what we're going to do now, so the first thing we're going to do, so now we are like actually setting things up and going through matrices. Okay, so the matrix is a bunch of numbers, square rectangle of a square grid of numbers. So we denote it this way: A11, A1n, A21, AM1, this is I throw. Jth column. Okay, and we write it in this way: Aij m by n. That means I runs from 1 up to mon. I goes from 1 up to m or 1 up to n. Are you guys like really lost?
Is that a question?
Huh? Yeah, I
So
was
did you
asking the I goes from 1 to m or 1 to n. The index I here.
1 to m?
1 to m, 1 to m. Okay. Okay, that was scary. Now so this is the matrix, and now so let's define the addition. So the definition we have A, so matrix with Aij, m by n, and B is also a matrix Bij, m by n. Okay, so we define the, remember, like we have the same m by n. Okay, so we define the matrix C to be A plus B, where C is given by Cij, Cij equals Aij plus Bij. Okay. So the addition is happening at entry wise. And you guys see that this is the like this is what happened in A level, but we are like 2, 3, 5, 9. So you're adding one entry from the matrix A with the one entry from matrix B. Okay. Good. And now, I mean, with this notation, we can actually, carry out computations and stuff. Okay. Now, so let's go here. So we have addition. Now, I mean, there are two other operations. Okay. But let's prove some things about matrices, matrix addition. So let me call M by N R to be the set. Let's look like this: Aij M by N, where each Aij is a real number. So that's the set. And we have defined a binary operation. In this case, that's plus. And that allows you to add two matrices. Okay? By above, right? So this definition. Yeah, Cij Aij plus Bij. Right? Now remember this plus. So now we can consider this. So this is M by N matrices over R, and then you have this plus. Okay, and this plus is different than the plus here. Okay, so this plus is about adding two matrices, and this plus is about adding two real numbers. Okay. Good. So now, do you guys know about product of two sets? If you have set A and if you have another set B, what is A times B? That's a set of ordered pairs.
We know how to calculate the product of two matrices.
No, product of two sets. So I mean, what it is. Typically, you have, I mean, we have seen this thing in like, you have graphs, right? So you have a bunch of elements in here. This is the A from the set A. And these are a bunch of other guys. These are the B's from set B. right? And then you have elements like this, pairs of elements, A comma B. And so the A times B is this set of ordered pairs where A is from A and B is from B. Okay. Now a binary operation is simply on a set S is a map, let's call it dot. It's a map from S cross S into S. Okay, it takes two elements from, let's call it A and B, and then you output something like this. Okay. So I want you to notice that this plus is actually something in here. So this big plus, it takes in two matrices, M by N, and outputs another M by N matrix. Okay, that's what the binary operation means. So there is something going on here. So in the other class, this class, it's gonna, even though I mentioned all the abstract stuff, it's algebra. It's gonna be like little computational, right? You will simplify things, and we kind of know that this should work, and it will work. Okay. But on the other hand, from the analysis class, you get a very thorough foundation on set theory and logic and all that. So this type of stuff get covered in there. Okay. Good. So there are, I'll write it down and it's there, and but you'll do things deeper in there, and we are not going to be using much like proof techniques and everything in here at the beginning, but at the beginning most of the stuff going to be like computational. Okay. Now first thing, so we can call this thing properties of addition. Okay. So we have first one is this operation plus is closed, meaning this: if we add two matrices, we add two matrices, we will get another matrix of the same type. Okay. So sometimes, I mean, this looks like very redundant, like very obvious, but sometimes when you define things and you don't get an object that you started with. For example, if you think about elementary row operations, okay, and you can multiply them, in the sense that what I mean is you can do one operation and then do a second operation after that. Okay, and then the combination of both of those two operations, you can define a multiplication in that way. Okay. But the problem is that multiplication is not going to be closed, in the sense that if you apply two row operations, one after the other, what you get might not be a row operation, elementary one. Okay. Good. So this looks very trivial in this setup, but in later cases, like this comes into place. Okay. And then the second property is this operation is associative. Meaning that A plus B, you can add two matrices, the first, and then add the third one. And this is same as okay. And let's prove this. Let me. So let A be an Aij, M by N, and B is Bij, M by N. And C is Cij, M by N. Okay. Now, so let's compute. It's called so if you have a, let's call this thing matrix D. Matrix C. So Dij is going to be ijth element of this guy plus the ijth element of C. Okay. Now the ijth element of A plus B is actually Aij plus Bij. Okay. Now, where are we at now? So what do you know about these pluses? Is this plus the matrix addition or the addition of real numbers? Real numbers. Now, the real numbers has this property. Okay? So you can use the property of the real numbers you go here. And the reason, because real R is associative. Okay, good. And then you can go like, okay, so this is Aij plus this is the ijth element of the matrix B plus C, right? So this should be the ijth element of the matrix E. Okay. So again, this is a simple computation, but we are not after using the property, right? So when you, like, we want to know why it worked deep down. Okay, so once you do this computation, you should be able to say, this associativity of the matrices works as long as the elements in the matrices come from a structure that's associative. Okay, good. So the associativity of the elements implies the associativity of the matrices under addition. Good. That's like this is not some computation and you do and you move on to the next one. And like this should open up and go like, oh, we can easily create matrices where the entries themselves are matrices. Okay. And it would be associative. Because the matrices are associative under R. Okay. And when they become elements, then yeah. So the note that so the n by n matrices with, see, like earlier I put R here. Right, that's where the coefficients are coming from. I can put 2 by 2 matrices here with R. Is also associative. Okay. Okay, so we are not moving on by doing this computation. Okay, we like figure out, okay, this is what went into proving this thing. So that means, so you go back up here and you look at the plus. Okay, here you go back here, go here. Okay, so you have the matrices ij, and here the elements aij come from, can be R, it can be C, can be a monoid. Okay, and come from something. If the entries can be added, then the matrices over those entries can also be added. Okay, that's the view. That's what I want. Okay, because you're not jumping into matrices and you're not simplifying things and like but you're like understanding what is the algebraic structures that actually responsible for these things. Okay, then you're using the building blocks. So this stuff that we have here. So in linear algebra, you have what you call algebra. So the m by n matrices that forms algebra. But that's too much. But most of the theorems, you don't need algebra. You'll be just using the monoids, groups, rings, and so on. So you want to kind of think of you're doing linear algebra, but you want to be kind of really figuring out what really happens inside. Okay, good. Now, so let's move on. So I proved that closed associativity and then identity. There exists their existent identity. Element. And this one is easy because proof of 3. We consider, call it O. This is the matrix with the Aij, m by n, where all the entries are 0. Okay. And then you can verify that for any matrix A from m by n, we have 0 plus A is equal to A plus 0 is equal to A. Okay. And this is called the identity element for addition. That's the one that doesn't do anything. Okay. And then the last one, for any inverse identity element, let me call it E, identity element 0. Okay. For A not equal 0, there exists a B such that A plus B equals B plus A equals 0. Okay. So if you take a matrix A and then you can consider if A is the matrix Aij, consider the matrix B given by Bij, where Dij is equal to minus Aij. Okay. So what we're doing, we're using this minus here. This minus is from the reals. Okay. Good. Now, if you have this thing, then you can show easily. Then A plus B equals B plus A is equal to 0. So that means you have a inverse. So we have defined the addition for groups, so addition for matrices, and then we have shown that the matrices with the addition satisfies these properties. Okay. Now, these properties, these four properties are the properties of a group. Okay. And I haven't shown you what the properties, what a group is, but this is the properties of a group. It's about, yeah. Have identity, and then you have inverse, and talks about monoid. Monoid is a binary operation that's associative and has identity. So the associativity, identity, and inverse. And the binary operation that take care of the closeness. Okay? So like it's going to be like language, but it'll take a while, but you'll start to talk that language. Okay? Okay, so what we have proved, so we have shown that it's a group. And sometimes this is all we need to like use. So like, but with matrices, the most interesting one is the multiplication, not the addition. Now, then let's do this thing. So what we have shown, but if you like really look into what really happened, so we use the associativity of the entries in here. Okay. Good. And also we use the inverse of the entry in here. Okay. So the exercise, let G comma plus, we write a dot. Okay. Let G be a group show that m by n matrices with the elements from this group is a group under its new operation. Let me call it tilde. Okay, so that's the operation that takes m by n matrices into itself. This is defined by A, B, this thing's ijth element is actually Aij, Aij. So this would be exercise 4. Now, there is a very important property of matrix addition. That's A plus B is equal to B plus A. Okay? And that's not a part of the property of the group. We didn't prove that one. Okay? So let me see, like with the groups, like if you think of the example with the row operation or the Rubik cube, if you do 2 row operations in one order and you do the same 2 operations in a different order, in the other order, you will get 2 different results sometimes. Okay? So that's not commutative. Okay? So show that in here. If is an abelian group, then is also commutative. So the commutative means AP equals BA for all A and B in G. Okay, and this is probably the main difficulty you run into, because everything would go like smoothly if you just think that you're working with R or something, but this property doesn't hold with matrices, and even in generally when you do algebra, you have to make sure that this works. Okay, so this exercise 5 tells you if the elements can be switched of the entries from the group can be switched, then the matrices like addition can be switched. Okay, good. Yeah, I think yeah, so we kind of talked about the matrices and matrix addition, and then we proved that like basic properties of it, but we did it in a kind of the minimal way. So you're not like working with R. If you're working with R, I mean, the R is included in this setup, but you want to be like very mindful about what we actually use it. Okay? And I mean, I'm doing this specially because I'll be doing linear algebra and then I'll be transitioning into abstract algebra. But if I do it this way, you will have you'll have most of the abstract algebra stuff, basics of the abstract algebra stuff covered already. Okay. So then I have added like the separate things for each of these topics, and I'll gather up the basic properties in those. Okay. I think so. Let me so I think I'm I have only 2 minutes. So let me tell you this story. Like, let's say you have an engine. Right? So like you're training like 6 cylinders, whatever, right? So you're not like when you learn these things, you're like a mechanic. I'm training a mechanic, and so you have to be able to go inside and then figure out, okay, so there's trouble in here, and if you fix that, this would work. Okay, so like when we learn a theorem, we're not interested in applying that theorem. Okay, that's not the main goal. So if I show you how an engine works, you're not interested in putting this engine in a car and like using it. So when you learn these things, the questions are about like what happens when you change something inside the engine. What happens if you change this? Can you change this and still get it to work? Okay, and if you're upgrading, and like what's the part that needs to upgrade? Okay, so like all these proofs, like if you look at a linear algebra book or like engineering book, whatever, you will just go over it and like you will not think about it. But I'm like, every time when something happens, you kind of want to identify this is what get used in here. And even though this has written in this way, this theorem, but the actual theorem is like something different. Okay, so this is actually the theorem that underneath matrix addition. Yeah, this exercise 4 and 5. That's all we need. Okay, so the entries has to be coming from a group, and if the entries are commutative, then the matrix is a commutative. Okay, and then when you define actually multiplication of matrices, that's going to be a different task. Then you need the entries to be coming from a ring, because you'd be adding and you also would be multiplying. Good. Okay, so I'll stop here. I'll end the recording, but I have some scary news. I ended the